in this example we want to find the partial fraction decomposition for a rational function whose denominator is a reducible quadratic function. So the first thing we're going to do is we're going to try to factor this. So we have x over x squared plus 23x plus 132. So this one is reducible. We can factor this. So let's try to think of two numbers that multiply to 32, or multiply to 132 and add to 23. Well, 11 times 12 is 132, and 11 plus 12 is 23. So we could factor this as x plus 11 times x plus 12. If you have difficulty factoring, you could also do the quadratic formula with a equals 1, b equals 23, and then c equals 132. And then if you did the quadratic formula, you would find that the solutions to, or the zeros of this function would be negative 11 and 12. And then remember, if you have a 0, x minus that number is a factor. So if negative 11 is a 0, then x minus negative 11 or x plus 11 would be a factor. And same thing, your other solution would be negative 12, which would tell you that x plus 12 would have to be the other factor. Okay, so now that we've factored it, we see that this denominator is actually two linear factors, two distinct linear factors, which means we will have two partial fractions, one with a denominator of x plus 11, one with a denominator of x plus 12. And remember, if the denominator of a partial fraction is a linear function, like mx plus b, the numerator is just going to be a constant. So some number a, and then same thing here, some other number b. Okay. And now we have to solve for these coefficients. So I'm going to treat this as my equation here. I'm going to first eliminate the fractions by multiplying both sides by the least common denominator, which is x plus 11 times x plus 12. So multiply both sides of this by x plus 11, x plus 12. So on the left side here, it would just cancel both factors. We'll just get x. And then on the right side, if I distribute the x plus 11, that will cancel this. And then if I distribute the x plus 12, I'll be left with a times x plus 12. And then if we distribute both of these to the second partial fraction, the x plus 12s will cancel, and we'll be left with b times x plus 11. Okay? Now from here, there's two methods we can do to solve for a and b. So I'm going to split this up and show you two ways to do this. So method 1 and method 2. So method 1 would be to distribute the a and distribute the b. So we would get x equals a times x plus a times 12, or 12a. And then distribute the b, we get b times x plus 11 times b. And then combine like terms. So we have, on this side we have 1x plus 0 equals, and on this side we have a plus b times x plus the constants 12a plus 11b. So what I did was I combined like terms here. We have two terms involving x, so if I factor out the x and then I add those, that's the same as a plus b times x, and then I just grouped the constants together, 12a plus 11b. So we know that if we have two polynomials equal to each other, then each coefficient has to be equal. So the coefficient for x, or x to the first power, has to be equal. So a plus b has to equal 1. And then the constants have to be equal, the constant terms. So 12a plus 11b would have to equal 0. So that gives us a system of two equations with two variables that we can solve. Now you could solve this using substitution or elimination. If you wanted to, you could solve the first equation for a or b and then substitute that into the other equation. What I'm going to do is I'm going to multiply this first equation here by negative 12 on the left side and on the right side. So now I would get negative 12a minus 12 times b equals negative 12. And then I'm going to add this to the second equation, 12a plus 11b equals 0, so that I can eliminate a. Negative 12a plus 12a cancels. Negative 12b plus 11b would be negative 1b equals negative 12 plus 0, which is negative 12. So we get b equals 12. And then I can substitute that back into this first equation here. A plus b equals 1. So a would equal negative 11. And then all we have to do is plug these coefficients back into the form of the partial fractions. So our partial fraction decomposition then would be a over x plus 11, so negative 11 over x plus 11, plus b over x plus 12. Okay. Now I'm going to go back and show you the second method for solving for these coefficients a and b, and you may find that this method is quicker and easier in some cases, like this one here. So for method 2, instead of distributing the a and the b, what I'm going to do is I'm going to plug in x equals negative 11 on both sides. So I would get negative 11 equals a times negative 11 plus 12 plus b times negative 11 plus 11. And if we simplify, that's negative 11 equals a times, this would be positive 1, plus b times 0. So b gets canceled. So we just left with negative 11 equals a times 1, or negative 11 equals a. So I plugged in negative 11 because I recognized that would make this factor 0, which would cancel off the b. I can do the same thing to solve for b if I cancel off a. To cancel off a, I'd have to make this factor equal to 0, which would require me to plug in x equals negative 12 on both sides. So on the left side, we get negative 12 equals a, and then this is going to be 0 plus b, and then negative 12 plus 11 would be negative 1. So again, that cancels. We get negative 12 equals negative b. So once again, b equals 12. So we get the same coefficients using the different method, but I think this method is a little bit quicker and easier. In any case, that is our partial fraction decomposition.